Hello, everyone, and welcome back to QNLP. Our next speaker will be Tull, who's going to speak about compositional semantics with formal concept analysis. Sean.
Okay, thank you. Are we definitely live right now? I thought it was still a minute early. Yeah. Okay. Thanks so much. Yeah, thanks to all the speakers so far and stuff for some really great talks. I'm sure there'll be more to follow. So yeah, this work's talking about formal concept analysis. So it's in the context of looking at new models of meaning for use in NLP tasks. Let's see this. Okay, so yeah, the motivation for the work is coming from this DiscoCat framework developed by Clark Kirk and Self-Duality. So this is basically a diagrammatic toolkit that lets you take some meanings that you've got for words built from some corpora or somewhere else, and then compute meanings of sentences using diagrams. And it's the basis for a lot of the approaches to QNLP we've been hearing about already today. So here, for example, we've imagined we've got meanings for these words Alice likes and Bob, and we're using some stuff about the grammar to build a meaning for the whole sentence. Mathematically, what's going on here is we're working inside what's called a monoidal category. And this is basically just a setting where we can talk about processes with these box diagrams, much like quantum circuits that we've seen in some of the talks already. And the words are given as states in this monoidal category. And standard NLP, you'd be taking your meanings of your words to probably be vectors of co-occurrence statistics. And today we're kind of thinking about using quantum models, so they'd probably be quantum states instead. But in this talk, I'm thinking about a different model based on this area called formal concept analysis. So given that today's supposed to be about QNLP, you might want to know why it's worth thinking about this other model. Well, again, arguably, you might want to use different models when you're doing different tasks in AI. And there's been lots of different formalizations of semantics across AI that are useful in different ways. So we've just mentioned two of them. So maybe the common one in machine learning is these vector models. And in this approach, each of these models is going to correspond to a different category that we can use the DiscoCat formalism in. So there's vector models, there's quantum models, which we're hoping will give us speed ups for doing lots of NLP stuff. So that's working in a category of quantum processes. Some other ones that are relevant here are there's a model called conceptual spaces due to an approach by Peter Gardenforth, and that's been studied in DiscoCat. And this is basically aiming to capture something about human cognition, for example, so be directly inspired by results from psychology and so on. And the way it works is by dividing things up into these different domains, such as tastes and sights and so on, like the sensory inputs that we get. So it could be useful for sense interfaces. And another model that's been explored at DiscoCat that's probably even simpler is just using relations. So that corresponds to the category of relations. And this is basically where the meanings of your words would just be sets and subsets. And so you can reason about them using quite classical style propositional logic. And at the bottom, there's just a picture that would be roughly like a state space for a word in each of these pictures, right? So we have vectors or a qubit and so on. The third picture is conceptual spaces. So it's basically good to explore different models for thinking about different aspects of AI and to draw on what people have done in the past. But ultimately, if we are going to relate these with quantum implementations, we do want to relate each of these models with these quantum models. So categorically, that means relating these categories to the quantum one. Either that's actually embedding the category in, or it could just be about taking whatever we found was interesting about this other model and thinking if we can represent it in a quantum way. So that's something to do in the future with what I'm talking about today. But the rest of the talk is just going to be talking about building another one of these new models for the DiscoCat framework to add to this list. So that means building a category where we can use these techniques. And the framework we're working in is formal concept analysis. So this is a popular framework in computer science due to Villa in the 80s and still used today. And it's got quite a lot of real world applications. Basically, what it lets you do is you have some massive data set, normally given in most simple form of a load of objects or things, like they could just be rows of your table. And they have a load of attributes. So they have some properties. And you've just got this big load of data. And what it does is let you extract a load of meaningful concepts, that they're called, that are going to help you talk about this data. And these concepts have a structure with them. Specifically, they form a lattice. So why do we care about this? Well, as we said, it gives us a new model where the word meanings have some structure. So they have some structure maybe different or beyond what you can do with just vectors. So they come with this lattice structure. What we can give back to FCA, hopefully, would be that you can use natural language to now reason about your data. So you have your data, you have this context, is what it's called, and you get this lattice of all the concepts to do with it. And we can now use these concepts as our meaning, so we can talk about them using sentences in natural language. That would be pretty great. So that's a quick overview. Let's now go into an actual formal introduction to formal concept analysis. So the object of study when you're thinking about this stuff is what's called a formal context. Okay, so that's quite a simple thing. It's a set G, which you call the objects, so they're the things you're talking about, and a set M, which are called the attributes. So these are properties that these objects can possess. And you just have a relation that just tells you which objects have which properties. So when G is related to M, you say the object G has this attribute M. So imagining like a big table of rows of your objects and properties of your attributes would be the columns perhaps. And what you do now is you're often talking about subsets, so sets of objects or sets of properties. So say a subset A of G. And you're thinking, okay, out of all of these objects, what are the properties that they have in common? And that would be this subset now A dashed of the attributes. So this is what attributes do they all have? Similarly with the attributes, you can say which objects have all of these attributes or these properties. And you know that B dash. So if you go A to A dash and back again, we call that taking the closure of your set A. So you'll see that coming up. This bar means taking the closure. And the point of FCA is that these closed sets are the meaningful ones. So you define a concept of your context to be a pair where you've got two of these closed sets. So they're given as each other's dashes in this operation. So A, which is called the extent of the concept. So that's a load of objects. And B is a load of properties, and that's the intent. So the idea is, here's a load of objects, and these are the properties that pick out precisely those objects. And conversely, those properties are precisely determined as they're the ones that these objects have in common. So that's the extent and the intent, and they each determine each other. So you can think about a concept in terms of which things meet the concept or what are the properties of that concept. And the result that gets FCA started is that these concepts always come with a structure. They form a complete lattice. So that means that they're partially ordered, and we'll just do that by saying one concept is below another when the object set of the first one is contained in the object set of the other, rather. So every instance of this one is also an instance of this one. So they're ordered under that, and they form a complete lattice. So that means you can take arbitrary suprema or infima of them. So they have a really rich ordered structure. And this thing is called the concept lattice of your context. I'll just denote it with this B of K. So K is your context, and B of K is the lattice. And FCA is about sort of studying these lattices, or how you can transform your context while keeping the lattice, i.e. the meaningful concepts, the same. So this is basically the main result that motivates the field. Just an example of what these contexts look like. So often you'll see them depicted in terms of a cross table, as I've alluded to already. So, and then you draw the diagram of its Hasse diagram like this, of the lattice, sorry. So on the left, we have the objects. So here there's just a load of bodies of water. And on the right, we have properties of these different types of bodies of water. And we put an X in whenever that body of water has that property. So a river is natural and constant, it says here. And from that, you build a lattice. So remember, each of these points of the lattice is a concept. So it should be denoted by a load of objects and a load of properties, but you often use this shorthand where you only write the minimal amount necessary to tell what you're talking about. So this one is just being written in terms of the objects, for example. And up here, so in particular, each unique type of object will basically give you one of these points at the bottom, unless they have exactly the same properties as something else. And each attribute will give you one near the top. Okay, so that's a quick introduction to FCA. So the goal was to build a category that lets us talk about this stuff. So we want to make a category now. The objects are going to be these formal contexts. So there's like the systems. And if you remember, the word meanings in this approach are given by states. So we want to make it so these states are given meanings that are concepts. So we want the meanings of words to be concepts in some context. And that means we need to make sure we can make these things into a monoidal category. So somewhere where we can plug boxes together and everything. So we have this restriction on the states in terms of what we want to do, but we don't have much else. There's actually some room in how you can define this. So it involved a bit of digging around to think about what is the best type of category to achieve this goal. And I'll just skip to what we ended up with. So there's this category that I'll call context when I say it out loud, but I've written CXT. So a category means it has a load of objects and it has a load of things called morphisms between them, right? So the objects are just going to be these formal contexts. So any formal context gets to be an object. And the morphisms are going to be certain relations between their sets of objects. So if we've got two objects, two contexts, K1, K2, you want to know what are the processes or the morphisms, so let me go between them. They're these relations. So they're basically just relations between the objects that preserve the interesting structure of the context. And that's captured by these two axioms down here. So they send each object of the first context into a closed set of objects of the second one. And they have this property that they commute with taking closures in a suitable way. Okay, if you've got these, just think of them as relations that respect the context on each side. Then you can compose them. So this tells you how the definition of your category has to say how you compose two of these. And you can use this rule. And you have to say what your identity morphism is, which is this. So one thing I just mentioned about this category is that the specification of what's an object and what's an attribute is essentially arbitrary, right? They're just sets. We could swap them around to get a new context, and that makes the category self-dual. A bit more down-to-earth way, it's just saying we've got a context, K, we can send it to this new one, K star, where we've just said, okay, whatever we called an object before, let's call an attribute, and whatever we called an attribute, we'll call an object in the obvious way. What's nice in terms of the category is that the way we specified it was in terms of objects, so it seemed a bit biased. It wasn't talking about attributes at all, but in fact, any one of these relations in one direction can be seen as the same kind of operation in the opposite direction, but talking about attributes instead. So there's this duality between objects and attributes. So our definition isn't really favoring one over the other. We can just flip the picture around and talk about attributes instead, if we prefer. And that corresponds to this sort of self-dual equivalence on the category if you're going to talk about it formally. Still, you might say, why are these the morphisms we've picked? We'll see what they correspond to structurally a bit more later on, but also just to justify it, several different authors have basically talked about this category either directly or implicitly, and without being aware of it, they seem to have sort of reached the same definition. In some cases, they're aware of it. So this category with these morphisms is the same as another notion of morphism between contexts that was actually described by some of the creators of formal concept analysis that they called a bond. So this is probably the most meaningful thing to justify our category, is that these morphisms do correspond to bonds, and these are developed precisely for doing FCA. They also correspond to another notion of morphism developed by Hideo Mori, who actually studied the category first in terms of what he called true correspondences, and as well as some other notions that have appeared in the literature. So this makes us feel like we might be on the right track with this definition. So I talked about how to make a category of these contexts now, but we are looking for a monoidal category. So we need to be able to not just plug boxes in a sequence, but also place them side by side too. So we need to talk about a monoidal structure on our category. So to give this, you need to be able to say what the trivial object is. So that's just like an empty diagram. And luckily that's easy here. But there's more than one way that you might want to define taking two contexts and placing them next to each other to build a new one. And that's the monoidal structure. So there's two different operations that are at least quite natural to think about. And I'll call them tensors. So the first one I'll call the lattice tensor. We'll see why later on. It's basically one that's best behaved sort of mathematically. So we take two contexts. We want to place them side by side to build a new one so that we can, eventually build big circuits where we're placing contexts all next to each other. So this is the way we define the new context. We take a product of the object sets, and then for attributes, we use a certain load of morphisms. So this means the set of morphisms in our category from K1 to K2 star with the following rule. And essentially, this definition is cooked up to make the tensor very well behaved. So it makes the category what's called a star autonomous category, which means that it basically has some of the ability to bend wires that we've seen in some of these perhaps in the talks already, but not the full amount. So it makes the category, it's not quite a compact category for those who know about those, but it is monoidal closed, and it does sort of have this star operation we've already seen. However, this tensor is basically defined from a mathematical perspective. If you wanted to come from a purely formal concept perspective, you might prefer this other one due to Villa, because this was directly made for doing FCA with, and it's called the direct product of contexts. So in some sense, it's simpler because we just do the products of both the objects and the attributes. It just has this slightly funny looking relation for when two objects satisfy property, it's true if either of them does. So this doesn't make your category star autonomous, so it's not closed even. So we don't have these kind of caps that you'll see in a lot of the Disco Cat work. So in the NLP stuff we've seen, but it does respect the star operation a bit more because this definition is sort of more symmetric between objects and attributes. So anyway, there are these two tensors around, and we kind of need to develop more examples to really pick out which one is best. But essentially, the first one is sort of the larger tensor that's easier to work with for the time being. One other thing I mentioned about the category to justify that it's not totally random is that it does correspond nicely with something to do with the lattices of these contexts. So if you have a context, you can take its concept lattice. And in fact, if you do this, this is giving you an equivalence of categories between the category you started from and this category, which I'll call SLAT. So that's where the objects are complete lattices, so complete sublattices. And the morphisms are maps between them which preserve all suprema of your lattice. Okay, so that's a mathematical thing that's just saying that the contexts, you can work with these contexts in this category as we do. It's basically exactly the same as working with complete lattices, for those who know about them, and these complete sub-preserving maps between them. So we can think either in terms of context or just in terms of lattices. And the fact that this is such an elementary category in terms of lattices suggests, okay, this is probably a natural notion of morphism over here. And each of the tensors you've got that I just talked about to make this category monoidal corresponds to a tensor over on this side too. And the first one that I called the lattice tensor is because when you take it over here, it's the usual thing that you'll find if you look up, sorry, this should say product here, the standard tensor product of sublattices. So it's the thing where if you look up how do you take the tensor of two sublattices, you'll find this in like an algebra textbook. And the one over here is a tensor of lattices that Viola studied as well, called the tensor product of complete. He just called it the tensor product of complete lattices. So he studied that in FCA. So this lifts over. So the work was in sort of finding this good category to set a foundation for studying formal concept analysis in this diagrammatic way. We've got started with that now. And hopefully this result lets you see that there is something canonical about what we've done. But the aim was not just to do mathematical stuff. We want to actually show that this category is useful for doing NLP tasks. This is certainly some work in progress, what we're doing now. So this is what we're currently thinking about. So this is all very, very likely to change, but I'd like to share with you just a couple of thoughts about it. So what we'll do is we'll just try and do an example. If this diagrammatic approach is actually going to be useful in FCA, it will presumably be because there is something useful about taking different contexts and placing them side by side in the pictures, or just like composing them with the tensors to build new ones. So it's about using these tensor operations. So we can imagine maybe that our noun space is built from some smaller contexts. So this is based on essentially lifting what was done with conceptual spaces. So this is the paper applying the Disco Cat formalism and building these conceptual space models within it, based on Peter Gardenforce's idea of conceptual spaces. I'm just going to lift the kind of example they were doing there. So here, let's say we've got a sort of color domain and a taste domain is the term. Just domain was the term from conceptual spaces. Here they're just contexts. So we have a context for colors, context for tastes, and there'll be a lattice for each. They're called C and T. And it doesn't really matter too much what they are, but here's just an example of what we could have as our lattice. There's some colors and properties of them, and some tastes forming lattice too. And for a noun, we're just going to give it a meaning as something composed of colors and tastes, because we're going to be talking about foods as our nouns, and we're just describing them in terms of their colors and tastes. So that means our context is given as a tensor of the context for color and the one for taste. And here we'll just make it simpler and use the equivalence with the category of lattices and just talk about the lattices rather than the context. So we're looking at a tensor product of these two lattices as being our space of nouns. So in this approach, right, words are interpreted as concepts, which are states in the category. Equivalently, in terms of lattices, elements of the lattice are the states. So a word like banana, it would be a state, i.e. an element of this noun lattice. And let's say for banana, we've got these two options, right? It can be yellow and sweet, or it could be green and bitter. So we construct the whole noun as something that's bigger than these two by taking their suprema. So nouns would just be states of our noun space. Verbs here, we're going to treat them like transformations on nouns. So something like tastes, for example, would take a noun and transform it And here it's just going to basically ignore the color and just leave the taste alone. And these are using these sort of discarding processes that exist in this category. And building on work that's been done in DiscoCat about pronouns, we basically want to model some logical words like, the banana, which, blah, 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 using certain extra features that we'll need in our category. So to treat something like which, we'll want something that behaves like a sort of updating mechanism, which we'll talk about shortly. And in pictures, it's just going to be this kind of dot. And so this state, the upside down dot, means sort of no information. So something X, which has property Y, will be given by plugging X and Y in here. And if you plug in sort of no information, it should just leave X alone. So I'll give you an equation like this. And now we can just give an example of computing the meaning of a sentence. And this is now totally generic. It's just a reasoning in a category where you have these dots around. So normally in DiscoCat, you'd see it done with these caps. Depending on which tensor we're working with, we might or might not have the caps here. But even if we do, it still might help to just rewrite this diagram in a simpler way without them. So we'll start from a version where we've slightly rejigged this in a way that would be equivalent in a compact category. But it's a bit more circuit-like. So now we're going to make it look like this instead. So banana's input here, which, and then the property goes in on the right. So this is a noun phrase that's going to modify our initial concept with some more information that's coming in on the right. And then we can just do calculations using the interpretations of the words I gave. So banana goes in here. So it's a noun, so it's living in color and taste. Which is this dot, but here there's C and T, so it's sort of a dot on each. Tastes I drew out before, so it kind of ignores the color and just looks at the taste. And the meaning of bitter would be the taste is bitter and the color we don't care, so that's we don't care dot here. And then as expected, what this actually computes to is just banana where we're updating the taste. So this is just this is how these calculations go. Now with the interpretation of banana we gave before, it's either yellow and sweet or green and bitter. And the way we constructed lattice at the beginning was that sweet and bitter will come out to 0 when we apply this dot, and we'll see why that is in a second. So we'd end up with green and bitter. So it's telling us that it's a green banana. It's not going to be the yellow one. So this is restricting from a general banana to this green one. And that's what the sentence has done for us. So why did the dot give us 0 here? Well, that's kind of what we needed to make this example work. So to generalize this now, to make it work for any lattices, we need to have these update maps around. And I'd say compare with this other work. It's recently been done by Wilson et al. On Safari of update structures. So what the dot was I had in mind there was this one, which you can do whenever your lattice is a distributive one. You can just make X and Y. So you take X, update it with Y. That would be X meet Y. It's the intersection in your lattice. You can do this, for example, in rel, which is in fact a subcategory of our category of contexts. But generally, to make it work, you need your lattice to be distributive. So we do want something like this. So we could either just only restrict to these distributive lattices, or otherwise we'll have to think about how to treat this, and that's what I'm thinking about now. So either we just require each context to come with one of these updates, or we try and do it instead using not the meets, but maybe the joins, which do always exist in our category, but they do behave in a slightly funny way if you try and make them work with these examples. I think the time's almost up. So I'll just say, clearly there's lots more to be done in implying this to QNLP. So we've done the foundational work in checking there is a category that's somewhat natural. We need to think about how to make it really useful in these NLP situations. Probably more studying of these update structures, I think, is a good way to go. And then we'll want to take it, adapt it slightly for some more real world applications where often your contexts aren't just binary, they have some quantitative data so that your table can actually not just be yes, no, but have numbers and so on in. I'd also be interested in seeing how it connects with conceptual spaces, as I said, and then of course, eventually how we can actually relate this to quantum models, either by just taking what was interesting about it or actually implementing these things in quantum systems and on quantum computers. Yeah, thank you.
Thank you, Sean. Thank you for the great talk. And so we don't really have much time for questions, but maybe I'll just ask a quick one.
Yep.
So, I mean, you've talked about how you compose nouns to form more elaborate concepts.
Yeah.
And what would the concepts for sentences look like?
Yeah, it's a good question. I don't have a really good answer for that, to be honest. I think that working in these categories will, I mean, it might end up being that the sort of circuit approach of DiscoCirc might end up being more natural. The meaning of because I know there that the meaning of a sentence would just be something that modifies the nouns that go in. And that seems somewhat natural. I think you have freedom here for picking a natural. So you'd want a formal context that describes, what different meaning sentences could have. And I think this would just depend on the application, really.
Okay, thank you very much. Thank you, Sean.